Hi, welcome all. Welcome to another chemistry class. In this video, we are going to review a rapid revision on the unit 6, that is thermodynamics. 6th chapter, first year topic, thermodynamics. Yes, a warm welcome to all in the video. Let's start. See the important topics that we need to go through in the chapter, as all of you know. The fundamental terminologies in thermodynamics. First of all, what is thermodynamics? Thermodynamics is basically dealing with the energy changes involving in a reaction. So during a chemical reaction or during a physical change, there are so many types of bonds, existing bonds which are broken and new bonds are being formed. So according to the nature of the bonds that been broken and the nature of the bonds that newly formed, either the reaction seems to be releasing the energy, we call it as exothermic reaction, or absorbing the energy, we call it as endothermic reaction. So the basic terminology in the chapter is exothermic reaction, endothermic reaction, known to all. What is exothermic reaction? Exothermic reaction, the reaction where the reactant is converted to product plus heat is liberated. So reactant converted to product and heat is liberated. That is called exothermic reaction. So what is endothermic reaction? Endothermic reaction. It is nothing but a reactant absorbs heat and is converted to product. A reactant absorbs heat and is converted to product, called endothermic reaction. So exothermic reaction, heat is liberated. Endothermic reaction, heat is absorbed. Right? Suppose I am expressing graphically. Can you identify which is exothermic reaction and which is endothermic reaction? This is energy axis and this is reaction progress. Energy axis along the x-axis and reaction progress along the x-axis and energy along the y-axis. Okay. Suppose I am plotting the two graphs. Are you been able to understand which is exothermic reaction and which is endothermic reaction? I am drawing a graph like this. This is reactant and this is product. I am drawing a graph like this. This is reactant and this is product. Which graph represent exothermic reaction? Which graph represent endothermic reaction? I am asking the fundamental points. Which is exothermic reaction? This or that? This is endothermic reaction. This is endothermic reaction and this is exothermic reaction. Quite simple to understand. During exothermic reaction, heat is released. That means the energy of the product will be lower than that of the reactant. While in endothermic reaction, heat is absorbed. Therefore, energy of product will be greater than that of reactants. So in exothermic reaction, we get a reasonably stable product because the energy is lower. In endothermic reaction, usually the product will be considerably, comparatively less stable because it is absorbing energy. Right? These are the basic terminology, important basic two terminology in the chapter. And the other terminologies, all of you may be remembering. What is meant by system? What is meant by surroundings? What is system and what is surroundings? What is a system? A system is a region under observation. A region under observation for experimental purpose is called a system. And the region other than system and system boundary, we call it as surroundings. Surroundings are close vicinity to the system. Suppose we are conducting an experiment in a test tube. the matter content inside the test tube, and this is called a system. And the walls of the test tube, we call it as system boundary. And the other region, we call it as surroundings. And system plus surroundings, we call it as universe. System plus surrounding, we call it as universe. I am sure all of you remember, system are of three types. One is called a open system, the other is called a closed system, and the third one, isolated system. Open system, closed system, isolated system. In an open system, we can see the nature of the open system is nothing but you can transfer both matter and energy. The transfer of both matter and energy are possible in a open system. What about a closed system? Transfer of matter is restricted while energy can be transferred. While isolated system, transfer of both matter and energy are restricted. A thermoflask is an example for isolated system, even though not perfect, but still it is called isolated system. While this is an open system, this is an open system, and if you are closing this entire, closing the mouth of the test tube, then it becomes a closed system, right? So open system, closed system, isolated system, surroundings. We are through the basic terms that is required in the chapter thermodynamics, right? Now, more on to the detail. What is meant by parameters? What are parameters? Parameters means measurable properties are called parameters. Measurable properties are called parameters. Pressure, volume, mass, temperature, all these are called parameters. And in parameters, there are microscopic parameters and macroscopic parameters. There is microscopic properties and macroscopic properties. If you are talking about mass, if you are talking about volume, if you are talking about such things, we call it as macroscopic properties. While if you are dealing with a bond angle in a molecule, if you are dealing with a bond length in a molecule, it is called microscopic properties. So there is microscopic properties and macroscopic properties. There is extensive properties and intensive properties. So properties can be classified into microscopic, macroscopic, then extensive properties and intensive properties. What is an extensive and intensive property? If you take mass, volume, etc., it is extensive property. Those property which depends on the quantity of matter present. That is called extensive property, and the property which does not depends on the quantity of matter, we call it as intensive property. For example, density. Density D is equal to mass by volume. We know density does not depends on the quantity of matter present. If you take 1 liter water and 10 liter water, density remain the same. If you take a small iron piece or a big iron block of identical nature, density remain the same. So density does not depends on the quantity of matter present, and it is called the intensive property. Always the ratio of two extensive property will be intensive. Or any extensive property taken for unit content, it is called intensive. Right? Volume is extensive, specific volume is intensive, like that. Okay? So properties, parameters, measurable properties are called parameters. There is microscopic properties and macroscopic properties, and there is extensive properties and intensive properties. Okay. Next is a talk on, all these are terminologies in the thermodynamics. Next is a talk on various thermodynamic processes. Various thermodynamic processes. What are the various thermodynamic processes? Right? All of you know, number one, it is called a isothermal process. Isothermal process. What is an isothermal process? A process where temperature change does not occur. It is constant temperature process. That is called isothermal process. T1 is equal to T2, thereby delta T is equal to 0. That is called isothermal process, all of you know. Number 2, adiabatic process. What is adiabatic process? Adiabatic process. Heat transferred equal to 0. There is no heat transferred. Q stands for heat transferred. Heat given to the system, heat absorbed by the system, that is heat transferred represented by small q. Right? Heat transferred is equal to 0. That is adiabatic process. There is no transfer of heat between the system and surroundings. That is called adiabatic process. Okay. Now, third one, isobaric process. All of you know what is isobaric process. What is isobaric process? Pressure remain constant. There is no change in pressure, called isobaric process. Next one, isochoric process. Isochoric process. What is an isochoric process? Isochoric process. Volume remain constant, no change in volume, no change in temperature. Isothermal process, no heat transferred. Adiabatic process, no change in pressure. Isobaric process, no change in volume. Isochoric process, so on. Right? Not over. There is reversible process and irreversible process. Reversible process and irreversible process. Unlike what the reversible, irreversible we discuss in the chapter equilibrium, a reactant converted to product completely and the product does not come back. That is an irreversible process. While reactant converted to product and product come back, that is a reversible process, what we discuss in the chapter equilibrium. Here, in thermodynamics, reversible, irreversible has got a slight different aspect. An irreversible process means all natural processes are irreversible in nature, which happens all of a sudden, which happens quickly. That is a irreversible process. If you compress the gas quickly, that is a irreversible compression. If the gas is expanding all of a sudden, it is a irreversible expansion. Meanwhile, what is reversible? You might have learned about. Reversible means a slow process, a process which happens infinitesimally slowly, so that at each moment of the reaction, the system and surrounding are under equilibrium. I will demonstrate. Suppose we take a PV diagram and we have a gas at pressure P1, at pressure P1 somewhere here, and we have the volume V1, right? Imagine the gas is suddenly expanded. The pressure is lowering suddenly. There is a sudden decrease in the pressure. You see P1 here suddenly dropped to P2. Thereby the volume suddenly increases to V2. So a sudden process that is called a irreversible process, and all of you know work done is equal to P delta V, and that is area under the graph. All of you know area under the graph is called work done, irreversible work done, represented by P delta V, right? What about a reversible process? What is the reversible process? Again, PV. We have a pressure P1 available here and V1, the corresponding pressure. Imagine the pressure drops very slowly, infinitesimally slowly. So what happens is there is the ideal process. It's an ideal process. The path traveled is like this, and you reach at V2. This is a rectangular hyperbola. PV isotherm. It is PV isotherm. It makes a rectangular hyperbola. And the area under the curve, it will be work done. All of you know work done is equal to integral PdV. Work done is equal to integral PdV. 2.303 nRT log V2 by V1. That is reversible process. Again, area under the graph, since it is a varying condition, we need to take the integration, and work done is equal to minus 2.303 RT log V2 by V1 for 1 mole of the gas. That is a reversible process, right? Sometimes some of you might have noticed the work done reversible expansion is greater than work done irreversible expansion. Work done reversible expansion is greater than work done irreversible expansion for a particular system, while work done irreversible compression will be greater than work done reversible compression. Try to understand yourself how it is possible, and is very simple by comparing the graphical plot of what you see here. You can easily understand. So what is the difference between ideal work and irreversible work? Irreversible work means which happens all of a sudden, and this is irreversible work of expansion, while reversible process is the one which happens infinitesimally slowly, right? It's an ideal process. At each moment the system and surrounding are under thermodynamic equilibrium, right? And the last one thermodynamic process that is also known to all, cyclic process. Cyclic process. A system traveling from one point, it is reaching to another point. Then from there it is reaching to another point. From there it is going to another point. And then finally it is coming back and repeats. You see, it's a PV diagram what you find. A system from state to 1 going to state to 2, then state to 3, state to 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's a cyclic process. Not necessarily 1, 2, 3, 4. 1, 2, 3 is enough minimum. It can be more than that. That's a cyclic process. A reaction travels all the way in a series of changes and finally come back to the initial state and then repeats. That is called a cyclic process. Okay. So these are the various thermodynamic processes. Okay. And our next topic is state of a system. State of a system. What is meant by state of a system? State means a condition. State means a condition defined by the parameters. Suppose we are talking about a gas is taken at a state 1 having pressure P1, volume V1, temperature T1, number of moles N1. A gas is taken state 1. This is called a state. Right? State means something like this. A matter is taken in a system having definite value of its parameters. It is defined by a parametric values. That is called a state of a system. So state is defined as a condition of the system defined by the parameters. P1, V1, T1, N1, that is defining a condition and is called a state. Okay. Now it go for a change in state. This is state 2. We get P2, V2, T2, N2 like that. Not necessarily all parameters should change. At least one parameter when changes, we say that the system state has changed. So the system changes from state 1 to state 2. And these parameters we call as state functions. Pressure, volume, temperature, internal energy, enthalpy, entropy, Gibbs energy, all these are called state functions, or they are called path independent variables. They are path independent variables. Their value does not depend on the path of the reaction. Rather, it depends on the initial and final state of the reaction. Whether the reaction is traveling in this path or the reaction traveling in another path like this, that doesn't matter. Whether it is traveling in path 1 or path 2, the properties, pressure, volume, temperature, number of all state variables, their value depends on initial and final state. Doesn't depends on the path of the reaction. And they are called path independent variables. Okay. Then what is a path dependent variable? Path dependent variable, there are two important path dependent variables. What are they? What are they? It is heat transferred and work done. Heat transferred and work done, we call it as path dependent variables. They decide the nature of the path of change of the system. Right, and there are four possibilities. Number one, Q, heat transferred, heat given to the system. Number one, assigned by a sign convention plus sign. Number two, heat liberated by the system, assigned by a convention minus sign. So heat given to the system, Q plus, heat liberated by the system, Q will be minus. Again, there are two other ways, work done on the system, which is plus, work done by the system, which is minus. So there are four possibilities by which a system changes from state 1 to state 2. What are they? Work done on the system, work done by the system, heat transferred to the system, heat liberated by the system. Heat given to the system, sign convention is positive. Heat liberated by the system, sign convention is negative. Work done on the system, sign convention is positive. Work done by the system, sign convention is negative. Right? Another very important parameter or a thermodynamic property we are talking about is internal energy. Internal energy, designated by the symbol U. Internal energy, and change in internal energy delta U. What is delta U? Delta U is equal to U2 minus U1, U final minus U initial. That is change in internal energy. What basically is internal energy? Internal energy is nothing but the various forms of energy that are available inside a given matter content. Right? Various forms of energy. Energy due to kinetic energy due to the molecular movements, potential energy due to the molecular bondings, electronic energy due to electrons, nuclear energy due to nucleus, various forms of energy available inside a system which are known and unknown, all summed up together, we call it as internal energy, also called intrinsic energy, designated by U, change in internal energy delta U. It is to be understood that absolute value of internal energy cannot be determined. Absolute energy of internal energy, absolute value of internal energy cannot be determined. State 1, we have internal energy U1. State 2, we have internal energy U2. You cannot determine what is U1, you cannot determine what is U2, but you can determine delta U. You can determine delta U. Delta U is equal to U2 minus U1. You cannot find absolute values U2 and U1, but you can find out delta U by an experimental process. You might have heard about it, is called a calorimetry experiment. Calorimeter experiment. Using calorimeter experiment, we can find out the change in internal energy. There are two ways of calorimetric experiment. One is at constant volume, one is at constant pressure. Constant volume experiment, we find out change in internal energy. And what is the name of that system? Anybody? Very popular one called a bomb calorimeter. Inside a bomb calorimeter, which is a constant volume calorimeter, we can find out the change in internal energy. And hope you remember the equation. Q is equal to mc delta T. Q is equal to mc delta T. A sample of matter which we want to find the change in internal energy is combusted, is burnt inside the bomb calorimeter, and the heat transferred from that matter is transferred to a water sample kept inside the system, and we measure the change in temperature of the water sample. This is change in temperature delta T, and this is specific heat of water, and this is mass of water, and mc delta T will be heat transferred from that matter content, and that is nothing but change in internal energy, and this is heat transfer equation, heat and mass transfer equation, right? And in the open condition also we can find out water calorimeter, open calorimeter, where we try to find out enthalpy change, a very prominent thermodynamic term that we are dealing with. So U1, U2 we cannot decide, but we can find out delta U, right? Now in the same context, we are learning the most important law in thermodynamics, That is first law of thermodynamics. First law of thermodynamics. What is first law of thermodynamics? All of you know this is law of conservation of energy. Energy can neither be created nor be destroyed, but can be transformed from one form to another. That is law of conservation of energy. Right? Here we can apply law of conservation of energy. I can tell you the final energy situation U2 is equal to initial energy situation U1 plus the cause of change. Cause of change is heat transferred and work done. So final energy U2 is equal to initial energy U1 plus cause of change. Why U1 changed to U2? Who caused the change of U1 to U2? U1 become U2 because of two properties, heat transferred and work done. Both are energy. Right? So what is U2 final? Final U2 is equal to initial U1 plus the cause of change. Nothing. Law of conservation of energy. Energy can neither be created nor be destroyed, but can be transformed from one form to another. Now on rearranging, you get U2 minus U1 is equal to Q plus W, delta U is equal to Q plus W. This is the mathematical expression for first law of thermodynamics. Very, 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 very important. Change in internal energy is equal to heat transferred plus work done. Work done, unless otherwise commented, we can take it as delta U is equal to Q plus P delta V. Because you know work done is equal to P delta V. So delta U is equal to Q plus P delta V. Is it clear? That is the mathematical representation of first law of thermodynamics. Right? Now imagine we are conducting the reaction at a constant volume. What happened to the equation? We are conducting the reaction at a constant volume, as I was commenting, the bomb calorimeter. What you get is delta V becomes 0 and you get delta U is equal to Q. We write it as QV. What is Q suffix V? Any thermodynamic property suffixed with another property means it is that suffixed property is constant. So this means delta U is equal to QV. That means it's a definition for change in internal energy. Change in internal energy can be defined as heat transferred during a thermodynamic process carried out at a constant volume. Change in internal energy, we call it as heat at constant volume. Heat at constant volume. Heat at constant volume. That means in an enclosed chamber. Many times we don't conduct the experiment in an enclosed chamber, rather we are preferring in an open condition where you can't apply this property. We need to go for a more relevant property, more commonly used property in thermodynamics, that is enthalpy. So next term is about enthalpy. So far what we have gone through is various fundamental terminologies in thermodynamics, first law of thermodynamics, various thermodynamic processes, change in internal energy, bomb calorimeter, finding experimentally delta U, how to find out, and a mathematical expression of change in, mathematical expression of first law of thermodynamics, that is delta U is equal to Q plus W, and the definition for delta U. Delta U, change in internal energy, defined as heat transferred during a thermodynamic process carried out at a constant volume. So what if at constant pressure? What if the system is kept open, that is constant pressure? We go for enthalpy. So that is enthalpy term at a constant pressure. Enthalpy term represented by H, and change in enthalpy delta H equal to H final minus H initial, that is H2 minus HI, that is H products minus H reactant, like that. Now what is this? H is equal to U plus PV. This is the relation. Enthalpy is equal to internal energy plus an additional amount of energy because the system is kept open. We call it as pressure volume energy. So H is equal to U plus PV. So what is delta H? Delta H is equal to delta U plus delta PV, very important relation. That is delta H is equal to delta U plus P delta V plus V delta P. Right? Since this is at a constant pressure, this is measured at constant pressure, this will be 0 and you get delta H is equal to delta U plus P delta V. This is the expression for change in enthalpy versus change in internal energy. Even you can write in the another format, delta H is equal to delta U plus delta N RT. What is delta N? What is delta N? It is sum of N gaseous products minus sum of N gaseous reactants. It is the difference between the total number of gaseous products, total number of moles of gaseous products minus total number of moles of gaseous reactants. Remember, only gases need to be considered. For example, if you take up the reaction PCl5 gas giving PCl3 gas and Cl2 gas, what is delta N? What is delta N? Delta N will be N products minus N reactant. What is N products? 1 plus 1, 2 mole. N reactant, 1 mole. You get 1. And what is the relationship? Delta H is equal to delta U plus 1 RT. Hope you understood. So when delta N is positive, sometimes delta N will be positive, sometimes delta N will be negative, sometimes delta N will be 0. Suppose delta N is positive, delta H is greater. Suppose delta N is negative, delta U is greater. Suppose delta N is 0, both are equal. Right? Very simple mathematical idea I am referring. It depends on delta N value. Suppose delta N positive means delta H is greater than delta U. Suppose delta N is negative means delta H is less than delta U. And when delta N is equal to 0 means delta H is equal to delta U. Very, very important application. Many times we are encountering questions based on that. And this formula, very, very important. Right? And you can also understand if delta U is equal to QV, delta H is equal to QP. Basically, both are same. Basically, both are heat transferred. One is heat transferred at constant volume. The other is heat transferred at a constant pressure. Internal energy is heat transferred at constant volume, heat at constant volume, and enthalpy is heat at constant pressure. Both are determined using calorimetric experiment. Is it clear? That is the primary first part of the chapter. Coming to the next segment, a very important term coming is various enthalpy terms. Various enthalpy terms. Various enthalpy terms. What are the various enthalpy terms? Number one, enthalpy of reaction. Enthalpy of reaction. Enthalpy of reaction. Enthalpy of reaction means enthalpy change during a particular reaction in which number of moles of reactants and products are as per the balanced chemical equation. Suppose we are writing 2H2 plus O2 giving 2H2O. Gaseous state, liquid state, standard condition. We call this as enthalpy of reaction. Rather, we give a degree like symbol, standard enthalpy of reaction. What is meant by standard enthalpy? All reactants are in their standard state. The value concerned is called enthalpy of reaction and it will be kilojoule per mole. Enthalpy, all enthalpy terms are expressed in kilojoule per mole. So enthalpy of reaction means Enthalpy change during a reaction in which number of moles of reactants and products are as per the balanced chemical equation. This is a balanced chemical equation, and that is called enthalpy of reaction. And if all the components are in their standard state, we call it as standard enthalpy of the reaction, which is indicated with that some degree symbol like that. Okay, standard enthalpy of the reaction. Enthalpy measured under standard condition. Hydrogen standard condition, gas. Oxygen standard condition, gas. H2O standard condition, liquid. That you have to ensure. So this is enthalpy of reaction. Number 2, enthalpy of formation. Number 2, delta H formation. What is enthalpy of formation? Enthalpy change during the formation of 1 mole of a compound from its constituent elements. You see, carbon in the solid state react with the oxygen in the gaseous state, and you are getting 1 mole carbon dioxide in the gaseous state. You can call it as enthalpy of formation of carbon dioxide. See, these enthalpies can be exothermic or endothermic. If it is exothermic, it will be negative. If it is endothermic, it will be positive. Enthalpy values, exothermic reaction, it will be negative. Endothermic reaction, it will be positive. Right? This can be plus or minus according to the nature of the reaction. You know, water formation is exothermic process. For this example, it is exothermic process, like that. All combustion reactions are exothermic process. This is enthalpy of formation of carbon dioxide. It's a combustion reaction. This will be exothermic in nature. Anyway, what is enthalpy of formation? Enthalpy change during the formation of 1 mole of a compound from its constituent elements. Carbon dioxide you can get in different way. But here, thermodynamically, what is enthalpy of formation of carbon dioxide? 1 mole CO2 formed from their constituent elements in their standard state. Carbon standard state is graphite, solid state, and oxygen standard state, gaseous state. So C plus O2 giving CO2, that is enthalpy of formation of carbon dioxide. So, enthalpy of reaction, enthalpy of formation. Next is enthalpy of combustion. Delta H combustion. It is the enthalpy change during the complete combustion of 1 mole of a given matter in excess of air. So, if you take methane in the gaseous state burned with the excess of oxygen, and you are getting carbon dioxide and 2H2O. This is in the liquid state and this is in the gaseous state. So how many oxygen? 2 oxygen, isn't it? 2O2, 2 plus 2. This is the balanced equation for the combustion of methane, and the enthalpy change will be called as enthalpy of combustion of methane. Enthalpy of combustion of methane. It is the enthalpy change during the complete combustion of 1 mole of a compound in excess of air. That is enthalpy of combustion. Normally, you know, enthalpy of combustion is always exothermic in nature. Right? So, enthalpy of reaction, enthalpy of formation, enthalpy of combustion. Then what? What next? Enthalpy of reaction, enthalpy of formation, enthalpy of bond enthalpy, several enthalpy terms, bond enthalpy, delta H bond enthalpy, energy required to enthalpy change during the complete cleavage of 1 mole of a particular type of bond. We call it as bond dissociation enthalpy. That is well explained in the chapter 4, bond enthalpy, well explained in the chapter 4, bond enthalpy. Then what? Enthalpy of neutralization. Enthalpy of neutralization. What is enthalpy of neutralization? It is enthalpy change during the complete neutralization of 1 equivalent of an acid with a base. If you take 1 equivalent of hydrochloric acid with 1 equivalent of NaOH, giving NaCl and H2O, the enthalpy of neutralization we call enthalpy of neutralization. It is enthalpy change during the complete neutralization of one equivalent of an acid with a base. There is something special in this case. Whenever you take a strong acid, strong base, whether hydrochloric acid NaOH, whether sulfuric acid KOH, the enthalpy of neutralization is invariably a fixed value, almost the same value. It is minus 57.3 kilojoule per equivalent, or minus 13.7 kilocalorie per equivalent, minus 13.7 kilocalorie per equivalent. That remained almost fixed whether you take hydrochloric acid NaOH, both are strong. Whether you take sulfuric acid and KOH, both are strong. A strong acid, strong base, the enthalpy of neutralization is almost fixed. Try to identify what is the logic behind it. Okay, number one. Number two, suppose we take a weak acid, suppose we take a weak base, the value will come down. The value will come down. You know what is the reason? Because for weak acids, there is no 100% ionization. There is no 100% reaction. For strong acid, strong base, there is complete reaction. That's why. Okay. And why the value is fixed? Think about and find out. Okay. That's about enthalpy of neutralization. Then there is various enthalpy of phase transitions. Enthalpy of various phase transitions. Phase transitions, that is enthalpy of fusion. Enthalpy of fusion, nothing but 1 mole solid. 1 mole solid is converted to 1 mole liquid. 1 mole solid is converted to 1 mole liquid at the melting point. The enthalpy is called enthalpy of fusion. Enthalpy change during the fusion of 1 mole solid to liquid at its melting point. What about enthalpy of vaporization? Enthalpy of vaporization, it is 1 mole liquid converted to 1 mole gas. That is enthalpy of vaporization. So, solid converted to liquid at its melting point, enthalpy of fusion. A liquid converted to gas at its boiling point, that is enthalpy of vaporization, right? While enthalpy of sublimation, hope you know, enthalpy of sublimation, a solid matter directly converted to gaseous matter at a temperature below the melting point, that is enthalpy of sublimation. So, enthalpy of phase transitions, enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation, various enthalpy of phase transitions. Similarly, there are various such enthalpy terms. Enthalpy of solution. Enthalpy of solution. 1 mole solute completely dissolving in the solution, forming a solution. Enthalpy of solution. Then various other enthalpy terms already we are learning in the lower chapters. Electron gain enthalpy, ionization enthalpy, lattice enthalpy, hydration enthalpy. Various enthalpy terms, all enthalpy terms, what is the definition and the critical, the nature of the reaction to be written, you must be aware of, because that's an important area which you will be applying in the numericals. Right? After learning this, we are going to discuss a very famous, very important law in thermodynamics applied in chemical thermochemistry. What is that law? Don't remember. It is Hess's law. Hess's law of constant heat summation. Hess's law of constant heat summation. Hess's law of constant heat summation. What is Hess's law? Hess's law states that the total enthalpy of a reaction will be same whether the reaction is conducted in a single step or multiple step. Or if you take a multi-step reaction, the total enthalpy of reaction will be the sum of enthalpies involved in the individual steps into which the overall reaction is subdivided into. For example, if you have a reaction R giving P, which is the overall reaction, which is a complex reaction happening in multiple steps. Step 1, R is first converted to A, we have delta H1. Step 2, A is converted to B, where it is delta H2. And step 3, B is converted to final product and it is delta H3. Then what is overall delta H? What is the overall delta H? You see, R is converted to P in 3 steps. R is converted to A is converted to B is converted to P with respective enthalpy values delta H1, delta H2, delta H3. What is the overall enthalpy of the reaction? All of you understand. Delta H1 plus, delta H2 plus, delta H3. So the enthalpy of overall reaction will be the sum of enthalpies of individual steps into which the overall reaction can be further subdivided into. Basically, what is this law? Basically, what is Hess's law? Hess's law is nothing but law of conservation of energy. Hess's law is nothing but law of conservation of energy. Right? Using which we can identify the enthalpy of certain step of reaction which we are finding difficult to conduct with. For example, you see carbon burning with oxygen, you get carbon dioxide. You can easily conduct in the laboratory. Carbon burning with oxygen, limited amount of oxygen, you get carbon monoxide. And carbon monoxide burns with oxygen, you get carbon dioxide. This is overall reaction. And this is step 1 reaction, this is step 2 reaction. Out of this, one step, we have a practical difficulty to conduct in the laboratory. It is nothing but the partial combustion. A partial combustion, you can't control and do it effectively in the laboratory. That means this delta H value, very difficult to find out. While this delta H value, you can easily find out. This delta H value, you can easily find out. Carbon monoxide converted to carbon dioxide. You can easily do in the laboratory. So this reaction practically we can do easily. This reaction practically we can do easily, but not this reaction. This reaction it is not easy to conduct in the laboratory. Without conducting, you can find the value. Suppose this value equal to X. This value equal to Y, you can calculate this value. How is that? Delta H is equal to delta H1 plus delta H2. This is value X, this is value Y. So what is delta H1? Delta H1 is equal to X minus Y. X you can find out in the laboratory, Y you can find out in the laboratory. Hope you understand. This is a practical application of Hess's law. And there is another law, sometimes you might have heard about Lavoisier-Laplace's law, Lavoisier-Laplace's idea. Which states that the enthalpy of a reaction, enthalpy of formation of a compound and enthalpy of decomposition of the compound under identical condition will be equal in magnitude with an opposite sign. Sir, what does that mean? Suppose A plus B giving AB, you have delta H is equal to plus X kilojoule per mole, then AB under identical condition, AB giving A plus B, delta H will be minus X kilojoule per mole. This is Lavoisier-Laplace's observation. When you reverse the reaction, delta H value becomes opposite sign. Right? All these things we are applying in the various thermochemical calculations. Okay. Now, another important application of Hess's law is Born-Haber cycle. You might have heard about Born-Haber cycle. Born-Haber cycle. A typical example of Born-Haber cycle is metallic sodium interact with the chlorine gas and you are getting NaCl solid. This is delta H, X kilojoule per mole. Right? This reaction, which is the overall reaction, happens in multiple steps. What are the multiple steps involved? Sodium solid is converted to sodium gas. We call it as enthalpy of atomization. Let the value be A kilojoule per mole. And sodium gas is converted to Na plus gas. That is called ionization enthalpy. Let that value be B kilojoule per mole. And Cl2 converted to Cl gas. That is bond enthalpy. Let the value be C kilojoule per mole. And chlorine converted to Cl minus gas. That is electron gain enthalpy. Let the value be D kilojoule per mole. Now Na plus Cl minus giving NaCl solid. That is lattice enthalpy of formation. Lattice enthalpy formation. Lattice formation. Let that value be, say, E. Now you can correlate X, A, B, C, D, E all together you can correlate, and any missing data if present you can work out without conducting the conducting the reaction. For example, you want to know what is the lattice enthalpy. You want to know what is the lattice enthalpy. Lattice enthalpy means amount of energy required to break 1 mole of lattice. This is what called lattice enthalpy. Suppose you want to know what is lattice enthalpy. It will be the opposite sign of E. If you get E, the opposite sign will be your answer. How to get E? Very simple. The overall enthalpy X is equal to A plus B plus C plus D plus E. With a small correction, A plus B plus C by 2 plus D plus E. Why C by 2? Why C by 2? This is bond enthalpy value C, kilojoule per mole. I have taken half mole chlorine. So it is C by 2. So it is A plus B plus C by 2 plus, I have written D, D plus E is equal to X. So you know this data, you know this data, you know this data, you know this data, you know this data. You want to get this data, you can calculate. Knowing all other data, you can find lattice enthalpy or any required property if you know the other properties. This is Born-Haber cycle. So application of Born-Haber cycle is based on Hess's law. So this probably is halfway portion of the chapter thermodynamics, more than halfway portion of thermodynamics. Very, very important area, very, very important points coming in this area. Many numericals are coming, you need to practice, and we are going to practice in the classes. Okay. Now on to the next segment of the chapter, we are going to deal with the second law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. What is the second law of thermodynamics? It is introducing the term spontaneous reaction, non-spontaneous reaction, entropy. All these terms are introduced by second law of thermodynamics. There are many statements given by different scientists for second law of thermodynamics. I will explain simply what is second law of thermodynamics. It is nothing but the natural flow of heat will be from a hot body to cold body. If you have a hot body which is in contact with a cold body, the natural flow of heat will be from a hot body to cold body. This is what the basic idea of second law of thermodynamics. And such reactions we call it as spontaneous reaction. What is a spontaneous reaction? A reaction which has a natural tendency to occur with or without initiation. That is called a spontaneous reaction. Heat can flow naturally from hot body to cold body. That is the spontaneous reaction. A piece of paper can burn naturally, but you need to give an initiation. So there are many natural processes which has a natural tendency to occur with or without initiation. If you take an ice block in the normal room condition, ice will melt. It's a natural process which does not require initiation. Burning a piece of paper, burning LPG, it is a natural process, spontaneous process, but you need to initiate. Hope you understand the difference. So what is a non-natural process? What is a non-spontaneous process? Non-spontaneous process means the reverse. This is a non-spontaneous process. Heat cannot be transferred from cold body to hot body unless there is an external agency. Without the aid of an external agency, this is an external agency. Without the aid of an external agency, you cannot transfer heat from a cold body to hot body. Hope all of you know what is an external agency which can cool down the material which is already cool. Refrigerator. Using refrigerator, this is possible. You can cool down a material which is already cool using refrigerator. So refrigerator like a system. An external agency can help you to do a non-spontaneous process. So this is a spontaneous process. This is a spontaneous process and this is a non-spontaneous process. Flow of water from a higher level to lower level is spontaneous process, while flow of water, we are pumping water from well to tank. That is a non-spontaneous process for which we need to have the service of a motor, a pump, electricity, everything is required. Hope you get the picture. Getting energy from a battery is a spontaneous process, while electrochemical plating is a non-spontaneous process. First one, you get energy from the system naturally, while the second one, you have to supply energy to the process. This is the difference between spontaneous and non-spontaneous process, which is talking about a term entropy. Entropy, a very important thermodynamic term. Entropy designated by S and change in entropy delta S. Unlike other thermodynamic properties, the absolute measurement of entropy can be taken. This is entropy and this is change in entropy. Change in entropy delta S is equal to Q by T, reversible amount of heat by temperature. That is change in entropy and the unit is Joule per Kelvin. That is the unit of entropy. What is entropy? Entropy, all of you know, it is the degree of disorder of a system. It is the degree of disorder of a system. Measure of randomness of a system. A gaseous matter has got a greater entropy than the liquid matter, which got a greater entropy than a solid matter. If you take water, if you take ice, if you take steam, ice has got a minimum entropy, liquid has got a greater entropy than ice, while steam, gaseous water vapor contain more entropy than liquid water. So measure of randomness, degree of disorder of a system is called entropy. Entropy is calculated by the formula reversible amount of heat by temperature. Reversible amount of heat by temperature, naturally it is 2.303 nR log V2 by V1, considering only a change in volume. Or there can be a adequate supplementary change in temperature versus volume, change in temperature versus pressure, that also can be incorporated, which is beyond the scope of the NCERT. So delta S is equal to Q by T. Q, you know, 2.303 nRT log V2 by V1. By T, it will be 2.303 nR log V2 by V1. Or in terms of pressure, P1 by P2. That's it. Okay. That is entropy of the system. Entropy can tell us regarding the nature of spontaneous reaction. And please understand, entropy, we need to make it clear, entropy of universe or entropy total. It will be delta S system plus delta S surroundings. Entropy of universe or total entropy can decide the spontaneous nature of the reaction. Please be aware of, when the total entropy of a process, is increasing, the reaction is spontaneous. While the total entropy of a reaction is decreasing, it is a non-spontaneous process. While the total entropy is zero, that is equilibrium. Please be aware of, for all natural processes, total entropy increases. For a natural process, entropy increases. That is a comment in second law of thermodynamics. This is the basis. So, for the total entropy of the reaction, positive, spontaneous, negative, non-spontaneous, zero, equilibrium. This is regarding entropy. This is regarding spontaneous reaction, non-spontaneous reaction, and second law of thermodynamics. What is a spontaneous reaction? Every process, natural process, which has a natural tendency to occur with or without initiation is called a spontaneous process. Then what is a non-spontaneous process? The one which has not a natural tendency to occur. It has to be driven. That is a non-spontaneous process. Finally, the chapter is dealing with the most important thermodynamic parameter, which was not known for the scientific society for a long period of time, and that was explained by Gibbs equation, Gibbs energy, that is Gibbs function G, and change in Gibbs energy delta G. What is Gibbs energy? Gibbs energy G is equal to H minus Ts. Gibbs energy G is equal to H minus Ts. H is total energy content. Now you can write delta G is equal to delta H minus T delta S, and this is conducted at a constant temperature and pressure. And this is called a Gibbs-Helmholtz equation, or simply Gibbs equation. Gibbs-Helmholtz equation, or called a Gibbs equation. Gibbs equation is referring delta G is equal to delta H minus T delta S. Right? And Gibbs energy is used for explaining the spontaneous, predicting the spontaneous, non-spontaneous nature of the reaction. How delta G predicts the spontaneous, non-spontaneous nature of the reaction? You see once again, if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous. And if delta G equal to 0, the reaction is at equilibrium. So delta G decreasing, Gibbs energy decreasing, that is a spontaneous process. Delta G increasing, that is a non-spontaneous process. Delta G equal to 0, that is equilibrium. How this equation we can understand simply, I will demonstrate. Please listen carefully. Imagine a ball is falling down. From a higher level to lower level. Imagine. I don't have to tell you, it's a natural process. A ball rolls down from a higher level to lower level. It's a natural process. It is a spontaneous process, isn't it? Yes. Now, there is no significance of change in entropy. A ball is a ball on top and bottom. There is no significance of change in entropy. Right? So there is no significance for this parameter. You please understand, delta G is equal to energy parameter minus entropy parameter. Right? A ball rolling down, an example where there is no significance for change in entropy, but energy, it is significant. You see, a ball at a higher level having a higher energy, falling to a lower level having a lower energy. So energy decreases. Now you see delta H. This is dropping. That means this is dropping. That means delta G is negative. That means it is a spontaneous process. Hope you understand. So for such an example, there is an energy drop. Energy drop means delta G will drop, and it is a spontaneous process. Okay. Let me tell you another example. Imagine you have a chamber given like this, separated by a partition, and there is a gas present here, which is gas A, and there is another gas present here, which is gas B. Just imagine, separated by a partition. What happens if you remove that partition? If you remove that partition, what will happen? If you remove that partition, it's very simple to understand. The entire gas will spread up. Right? The gas molecules will be spreading throughout the system. The gas molecules A and B will be spreading throughout the system. Right? Here, there is no much change in energy. Suppose it is happening over a controlled system. There is no much change in energy, but there is a change in entropy. What is happening by this to this? What is happening by the entropy term? Entropy increases or decreases? Entropy increases. Why entropy increases? Two gaseous system mixed up. So the degree of disorder increases. Entropy increases. Now you apply the formula. Delta G equal to delta H minus T delta S. No much significance for this, but entropy decreases. So this is decreasing. This decreasing. Sorry, entropy increases. Sorry. Entropy increases. So it is entropy increasing. Entropy increasing means overall this value is minus. Minus increasing. That means delta G is decreasing. Once again, it is delta G decreases. It is a spontaneous process. And I don't have to tell you, this is a spontaneous process. By the time you remove the partition, A, B gases will mix up. Isn't it? So it is a spontaneous process. So here it was spontaneous in terms of dropping energy. No significant change in the entropy. Here it is a spontaneous process by increase in entropy. No much significance for the energy. So two things very important for deciding entropy, spontaneous nature of a reaction. Drop in energy, that is exothermic process, and increase in entropy, increase in a delta S positive process will be highly favorable for a reaction to be spontaneous. Let's have a look at the various predictions that we can do for thermodynamic operations. Basically, there are four types of thermodynamic operation: delta H, delta S, delta G, and nature of reaction. Let us see. Delta H, number one, it is an exothermic process, delta H negative, delta S negative. Number two, it is an exothermic process, delta H negative, the entropy positive, the entropy increases. Number three, it is an endothermic process where entropy increases. Number four, it is an endothermic process where entropy decreases. These are the four thermodynamic possibilities. Number one, exothermic reaction where entropy decreases. Number two, exothermic reaction where entropy increases. Number three, endothermic reaction where entropy increases. Number four, endothermic reaction where entropy decreases. There are four possibilities. Let us try to understand how delta G comes. How delta G comes? You see that delta G equal to delta H minus T delta S. So this is minus, this is minus, this is minus, this is minus, means minus of minus, this will become plus. Minus of minus will become plus. Now delta G can be either negative or positive. So delta G is negative when delta H is greater than T delta S. That means at a low temperature. At a low temperature, delta G is negative and the reaction is spontaneous. While when the temperature increases, delta H is less than T delta, this will dominate. That means at a high temperature. At a high temperature, this value will dominate and delta G will become positive. And the reaction is non-spontaneous. I am referring the first situation. So such a reaction, exothermic reaction where entropy decreases, it is spontaneous at a low temperature and non-spontaneous at a high temperature. At a high temperature, At high temperature, this value will increase and delta G will become positive. Hope you understand. What about the second case? Delta H negative and delta S positive. Delta H negative and delta S positive. So the basic equation is delta H minus T delta S. This is negative and this is positive. That means both are negative. That means delta G is negative always and the reaction is spontaneous always. Most favorable situation for a reaction to be spontaneous. Few minutes back I told. Now the third one. This is positive and this is positive. That means this is positive and this is positive. This is positive means this minus will remain. That means delta G can be either plus or minus. Delta G is negative when delta H is less than T delta S. That means at a high temperature. At a high temperature, this value will dominate and delta G will become negative and the reaction is spontaneous. Just opposite to this. And delta G will be positive, that is delta H greater than T delta S at a low temperature and the reaction is non-spontaneous. That means just opposite to this. And the last one, delta H positive, delta S negative. This is positive and this is negative. Delta S is negative. Now you see this is positive, minus of minus, this also. So both will become positive and delta G is positive always. And such a reaction is always non-spontaneous. The most unfavorable situation for a reaction to be spontaneous. This is most favorable situation for a reaction to be spontaneous. Exothermic reaction where entropy increases. Most favorable. Endothermic reaction where entropy decreases. Least favorable for a reaction to be spontaneous. Very, very important explaining, predicting the nature of reaction, nature of spontaneous nature of the reaction. Right? Let me tell you last one formula from the chapter to conclude the thermodynamics. What is that formula? Many times you need to operate that in various numericals. Delta G is equal to delta G naught plus 2.303 RT log QC. This is the formula. Delta G is equal to standard delta G plus 2.303 RT log QC. What is QC? That we are learning in the chapter equilibrium, reaction quotient. Now you see what happens at equilibrium. At equilibrium, what happens? Delta G becomes 0 and at equilibrium QC becomes equal to Kc and thereby you get the relation. This becomes 0 and this becomes Kc. You get the relation delta G naught is equal to minus 2.303 RT log Kc, or delta G naught is equal to minus RT ln Kc. Many times we encounter this formula for doing the numericals, right? That is delta G naught versus equilibrium constant. Okay. This is the major discussion that happens in the chapter equilibrium. We started from the basic terminology, first law of thermodynamics, internal energy, enthalpy, various relations concerned, various enthalpy terms, Hesse's law, Born-Haber cycle, then entropy, second law of thermodynamics, entropy, spontaneous, non-spontaneous, finally Gibbs function, and predicting the spontaneity of the reaction using the most important hardcore content of thermodynamic property, that is Gibbs function. And finally Gibbs function versus standard Gibbs energy versus equilibrium constant expression. These are the important topics from the chapter thermodynamics, with which we conclude the video, we conclude the class. We'll meet with another class in another chapter. Okay, bye, take care, see you.